For general plane motion, we can simply apply these equations of motion that we learned previously. In this case, the total moment is summarized about an arbitrary point P, and it equals to the total kinetic moment about the same point P. Or its alternative form, that the resultant moment summarized about the gravitational center point G equals to simply Ig alpha. Let's look at this example. When we are analyzing the general plane motion of this wheel, we need to recognize that there are two possibilities. One, this wheel is rolling without slipping. Two, the wheel is rolling and slipping at the same time. We need to do calculation and draw a conclusion, which is the case. Is the wheel rolling with slipping or not? Let's look at the first situation, assuming slipping does not happen. We draw the free body diagram of this wheel. It is subjected to the applied couple moment, its own weight force, normal force from the ground, as well as the frictional force exerted by the ground to the wheel. And it is important to determine the direction of this frictional force. Now, when this wheel is rolling under this couple moment, at the point of contact, the impending motion of the wheel is to the right. Therefore, the frictional force exerted by the ground to the wheel points to the left. And this completes the free body diagram, and we can draw a simplified version of the kinetic diagram, recognizing that there is no motion along the vertical direction. And now we are ready to write our equations of motion. Resultant force along the x direction. There is only one force along the x direction, which is the frictional force, and that equals to the mass of the wheel times the linear acceleration of its gravitational center along the x direction, agx. Resultant force along the y direction equals to 0. From here, we can solve for the normal force, which is the same in magnitude as the weight force, which is 177 Newton. And then, for the resultant moment, recognize that when there's no slipping, the point of contact is indeed the instantaneous center of zero velocity. And also, the forces W, N, and the frictional force all pass through this point. Therefore, it is most convenient to summarize the resultant moment about this instantaneous center of zero velocity, and that equals to IIC alpha. There's only the 80 Newton meter couple moment in this equation, and for IIC, it can be determined through the parallel axis theorem again. Ig is determined through the radius of gyration. Therefore, from this equation, we substitute in all the known parameters, and we can solve for alpha to be 13.1 radian per second squared. Now, if you recall, we discussed an example before of a rolling wheel, and when slipping does not occur, we draw the conclusion that the linear acceleration of its mass center simply equals to alpha times r, the radius of this wheel. Therefore, since we're assuming no slipping in this situation, we can apply this equation directly and calculate the linear acceleration of the mass center of this wheel to be 6.54 in the unit of meter per second squared. From here, we can solve for the frictional force as well, which is 118 Newton from the first equation. However, how do we determine if slipping occurs or not? If this frictional force exceeds the maximum static friction, which is calculated by mu s times normal force, then it means that slipping does occur. In this case, the frictional force calculated is 118 Newton, but mu Sn is only 58.4 Newton. Therefore, in this case, we can draw the conclusion that slipping does occur, and the frictional force between the wheel and the ground is actually kinetic friction. Now let's do the calculation again, knowing that slipping does occur. The free body diagram and the kinetic diagram look the same as in the previous step, with only one exception. Now the contacting point between the wheel and the ground is no longer the instantaneous center of zero velocity, because at this contacting point, since the wheel is slipping, it no longer has the linear velocity of 0. With that said, now let's write our equations of motion. The first equation, same as earlier. Second equation, same as earlier. But for the third equation, we cannot summarize the resultant moment about instantaneous center of zero velocity anymore, since we do not know where that is. So let's just go ahead and use this general equation that the resultant moment summarized about point G equals to Ig alpha. Now we have not only the 80 Newton-meter couple moment, but the frictional force also has moment about point G. And Ig is calculated through the radius of gyration again. At this point, you might notice that we need one more equation in order to solve for our unknowns. The equation that we used in the previous step, that Agx equals to alpha r, no longer applies, because once again, that equation only applies when slipping does not occur. But since slipping does occur in this case, we know that the frictional force between the wheel and the ground is now kinetic friction, and kinetic friction is always calculated by this equation, mu k, the coefficient of kinetic friction, times normal force m. Therefore, we can simply calculate the frictional force to be 53.1 Newton. Substitute into the first and the third equation, and we can solve for the linear acceleration of the gravitational center to be 2.95 meter per second squared, as well as the angular acceleration of this wheel to be 33.0 radian per second squared. And that completes this problem.